As I presume he was saying, I'm Jasiel Spelman. This is Exploring the Safari, and I usually go by Wandering Glitch. That's usually the handle I try to be credited by. And just to give a quick overview, I'm going to, agenda, I'm going to give a quick overview as to like why I'm giving this conversation. I'm going to do some kind of basics about the JavaScript Core architecture. And JavaScript Core is the JavaScript implementation within WebKit, within Safari. I'm going to go over some vulnerability case studies, and then, time permitting, we'll go over questions. And this image on the right over here is one of my favorite things about several browsers, in that if there's a crash, if there's an access violation, it'll very friendly and nicely retry the exploit for you and give you another shot at actually surviving and getting code execution. I think Chrome does not do it. So as I was saying, I'm Wandering Glitch. I'm part of Trend Micro's Zero-Day Initiative program, and I am one of the vulnerability researchers on that team. Most important thing here is just that I help run and organize the Pwn2Own hacking competition. So anyone that saw Marco present on Amatkama's bug earlier, that's the type of stuff that we see at Pwn2Own. Outside of that, I try to spend a lot of time doing reverse engineering and static analysis of various applications. And for that, I actually got some grief from my friends when I started looking more into WebKit because it is open source, but I'll touch on that in a little bit. So just as a quick overview, one of my coworkers is named Simon Zuckerbraun, and he initially was a researcher submitting vulnerabilities to the Zero-Day Initiative. And when he joined, we kind of have an internal debate as to how he was finding the vulnerabilities. He was finding them by statically looking at Internet Explorer, and basically just looking at MS-HTML to look for various code patterns to try and see where things were done in a improper, weak manner. And as part of this, when we finally hired him, we asked him to do an internal presentation. And one of the things he said there very much stuck with me, and it was that browsers break perfectly normal C++. And he gave an example of code that looks similar to this, where you have a this object, and then you have a member that you're accessing, and then you're calling some function based off that member. And this is a perfectly normal and typical pattern that you'll see in C++. But if you're dealing with a web browser, this could be very unsafe, because if that function happens to end up calling JavaScript, it could break assumptions about the lifetime of the instance variables that you're accessing. In a very, very similar vein, JIT breaks perfectly normal JavaScript, specifically because objects are the bane of JIT. This applies largely to Chakra and to Safari, but it also applies to V8. Firefox, for some strange reason, seems to have been the most resilient to this type of attack. But here we have an example snippet of code, and this was used as part of, I want to say, 360 Chihu's attempt on Safari. And it doesn't look too strange. It looks a bit worthless as far as functions go, but it's not that interesting. Like we have an array A, or an array-like object that we are performing writes of floating point values to. We have this B variable that we're reading a value out of A and writing to. And then we have this math.clz32, which is operating on C. What you don't realize is that because of the way Safari works, this is actually taking advantage of an exploitable condition that results in type confusion and lends itself to a very, very clean read and write primitive, and thus is very, very easy to exploit. It looks simple, and it's kind of hard to see just statically, but it's very, very nice and great for exploit reuse as well. Another thing is I'd mentioned WebKit is open source and that I had gotten grief about it. I live in Austin, Texas, and we have a fairly good security scene, and we have monthly security meetups. And one of my buddies was saying that, hey, you spend most of your time writing IDA-Python, reversing various applications. Why go after something that's open source? And part of it is because, although it's open source, there's still a lot to it, and there's also lots of acronyms that don't really make sense. And so, not sure how many people will see this. This is kind of an older acronym from the internet, but OMG WTF BBQ is an acronym that used to be used in a lot of memes. And if you look at WebKit, it ends up being optimized machine code generation, web template framework, and build block quickly. Just because, well, there's all sorts of all sorts of various types of acronyms. There's also one for LOL, but I don't actually remember what it stands for. And it's more DOM specific than anything else. So now I'm going to go over some high-level details about the JSC architecture. The main thing here I want to cover is what type of variables are used to hold various values, but then also some of the array types, as those are the two things that you need to know to understand how JIT bugs end up, or how these type of JIT bugs end up being so very exploitable. So in JavaScript Core, there's a notion of a JS value, which is a tagged nan-boxed value, where you have all the values basically being determined or being treated as not a number values. The type is determined by the upper 2 bytes, where if the upper 2 bytes are all null, then the rest of the value is treated as a pointer. If the upper 2 bytes are FFFF and the next 2 bytes are 0000, then the lower half of the value will be treated as a signed 32-bit value. And then anything in between is going to be treated as a double, but doubles are a little bit special. Specifically, 2 to the 53rd power will get added to it, and I'll give an explanation as to why in a couple of slides. But here we have a couple of examples of what these values might look like. So if we have a pointer to hex 1, 2, 3, 4, 5, 6, 7, 8, the upper half is going to be all nulls. The lower half is going to be that pointer value, though it could be 2 bytes larger. If we have 1.5, we're going to have the floating point decimal value for that, but it's going to have 2 to the 53rd power added to it. And I'll show that more in a slide or two. And then if we have the value 1, that's an integer that can be represented as a 32-bit signed integer. So the upper half is FF00, or FFFF0000, and then the lower half is the interpretation of 1. Now we'll talk about arrays. There are 4 or 5 different types of arrays within WebKit, but there are 3 that we really care about, and one in particular that is very, very important. The first one is pretty boring. It's an array with int32, which, as the name kind of implies, is an array with 32-bit integers. Basically, half of the space in arrays of this type is completely wasted, because the upper half is always going to be FF0000, whereas the lower half is going to be the actual values that we care about. We have array with double, and this is the most important type, specifically because these are values in their native format. That is to say, they're not as JS value tagged values. And then we have array with contiguous, and that's basically a continuous block of memory, just as the other two. But in this case, it's expecting to only have tagged values, and it in particular expects to have objects or int32s or floating point values or basically anything. So nothing too interesting. But now there's also conversions. So you can have an array with int32 that gets converted into an array with contiguous. You can have an array with double that gets converted into an array with contiguous. So if we have it right, sorry, backing up, the reason or the way that happens is you perform a write that will force a type coercion on it. So if we write the 1th index to the array with int32, then the second value ends up being a pointer to whatever this object is. If we do the exact same thing to the array with double, we now have kind of the similar situation, except now we have that 3FF8 becoming 3FF9, because as I was saying a couple of slides ago, doubles are special, and when they're in their tagged format, 2 to the 53rd power gets added to it. Just to kind of drive that point home, there are floating point values that you can use that look like pointers. For example, here we have this array with double. It's a normal array with double. There's nothing wrong with this, where the first 2 bytes are zeros and the rest is a value that we have completely under our control. And the second value is the value for 2.5. And when we modify it, we now have, there we go. We have 1 being added, so it cannot be interpreted as a pointer. The whole issue here is that with a lot of JIT vulnerabilities, we're able to break that assumption and get writes performed where that 1 will not get added, so that our values will be treated as pointers, and then bad things can happen. Now I'm going to give a very kind of quick and brief timeline as to how execution of JavaScript occurs within Safari, within WebKit, within JavaScript Core. There's a notion of a parser, which will take the actual JavaScript and then lift it into parse it into a abstract syntax tree. From there, it'll go to a byte compiler, which will go through that abstract syntax tree and turn that into bytecode. The bytecode then gets handed over to the low-level interpreter. That's where execution of JavaScript actually begins. And then it will move on to the baseline JIT. From the baseline JIT, it'll go to the DFG, which is data flow graph. This is the first place where actual performance improvements will really get made. And then it'll make it over to the faster-than-light engine. And to give a little bit more detail and context for all of them, the parser has two parts, a lexer, which just converts scripts into tokens, and then the parser itself, which converts tokens into the syntax tree. If you have, say, an excess number of closing parentheses or closing curly braces, the lexer will catch it, but any sort of other grammar-related things will only be caught by the parser itself. So if you have if, while, true, if, while, that won't be caught by the lexer necessarily. That will get parsed by caught by the parser. The byte compiler, as I was saying, consumes the AST and produces an internal bytecode. As far as vulnerabilities go, I only know of one or two that have actually really affected here. The triggers for them were in the later layers, but the bugs themselves happened here during parsing or during creation of the bytecode. And then there's the low-level interpreter, which, as I was saying, is the first to start executing code. It does not care about speed of execution at all. What it tries to do is start running and executing things as soon as possible. It also starts collecting some metrics so that it can feed the data to the lower levels, or to the faster engines. One very, very important thing about all the engines, or all the layers from here on out, is that there's a notion of something called an OSR entry and exit. That stands for on-stack replacement. All of the low-level interpreter, the JIT, the DFG, and the FTL all use the exact same calling convention. And the nice benefit of this is that if you are ever in a spot when you're in one engine and you want to tier up or tier down, you can do so by just OSR exiting or entering into one of the other layers, which makes it very, very nice for quickly saying, hey, I have this bytecode, I can't handle it, we need to go back. Or, hey, we keep bailing out of this one instruction, let's completely bail and just completely tear down what we're doing here. It also collects metrics for feeding into the other layers, and JIT all occurs in another thread. Again, so that the low-level interpreter's execution is going to start and occur very, very quickly and not be delayed by creating and instantiating a JIT. The baseline JIT itself only will optimize function calls. It does nothing else. Not entirely sure why they took this approach. It does collect more data, but this will only impact things where you have some JavaScript that calls a lot of functions. If you have a while loop that is doing a bunch of math or anything like that, this baseline JIT will do absolutely nothing for you. There'll be no performance improvement whatsoever. Oops. Cool. Now we have the data flow graph. This is the fastest sublight engine. It's really the only sublight engine, and it applies classic compiler optimizations, loop invariant code motion, blanking on everything else. But this is where you actually have real optimizations. As part of that, some function calls will get completely optimized out and replaced with intrinsic versions. And the name for functions of this nature are all called intrinsics. That snippet of JavaScript I showed a few slides ago with math.clz32, that was the result of an intrinsic that was not properly modeled. Bounds checking removal also occurs here, and array type check removal also occurs here. And although that may sound dangerous, it actually does make a lot of sense and can be a great performance win. For example, if you're writing to an array from 0 to 9, you don't need to check over and over again for each of those writes that it is actually an array of size 10. You can just check once, and then you can know that those are all safe. Again, if you're only writing, say, floating point values to an array with double, you don't need to check over and over again that your input value, which you already know is an array with double, is actually going to be written to an array with double. You can just say, you can just check that once and then continue on with all your writes and not check more than once, allowing for better performance. In order to support things of that nature, you have to safely model operations. And they have two ways of doing this within JavaScript Core, within the DFG engine. There's the DFG abstract interpreter, and then there's the DFG clobbereyes. They both do slightly different things, basically checking to see that is it safe to do array type check removals, and is it safe to do bounds checking removals? There's actually a few other things, but those are the main things that we care about when we're looking for bugs, when we're trying to take advantage of things. And so we have this example on the left where you have a massive switch statement, several cases, and they all end up reading world and writing heap, and that is the DFG clobbereyes way of saying, we don't know what this operation will do, just assume it's going to break all assumptions we have about how we're running, how we're operating. On the right side, we have set function name, and then we have this clobber world. That's going to do the exact same thing, and that's going to say, hey, let's break all assumptions about everything we've taken up to this point. As far as we know. So if we're within a function, break all assumptions that we've made within this function after this point, because we can't be sure that any of our assumptions will hold. We need to recheck everything. Lastly, there's the faster than light, which uses special backend. It's the B3 bare bones backend assembly IR. It used to use LLVM as a backend, but that turned out to be very, very bad for performance, specifically because LLVM is great for optimizing entire programs, not so much for optimizing functions at a time. If you do any sort of WebAssembly, that compiles straight to B3. And one interesting note that I don't fully understand why they chose this, all integers in the FTL are treated as signed integers. And that will come into play a little bit later. As far as vulnerabilities go, most of the ones I've seen have been in the DFG engine. I can only think of 2 that have really affected the FTL. And one is kind of, it triggers in the FTL, but we'll talk about that in a little bit. So the first true vulnerability I'm going to go give a deep dive about is CVE 2017-2547. This was brought to us by TenSec. TenSec Keen Lab during Pwn to Own, I think 2017 at TenSec. And if we look at the crash, we see that we have exe bad access with an address 41, 41, 41, 41. Interesting thing when you're looking at the trigger is that there's no 41s anywhere to be seen. If we look at it a little bit more, we'll see that we have a for loop where we're calling this bar function 5,000 times. Within the bar function, we have this for loop that is iterating 20,000 times, and it does absolutely nothing. The whole point of this is to get the function bar to be DFG'd and then to be FTL'd. The way that the tier up happens from various engines is based on function hit count, but also loop hit count. So if you have a particular function that is being called a lot of times, that can trigger a tier up into one of the faster layers. Additionally, if you have a for loop, or any sort of loop, a while loop will work as well, where you're looping over the same code over and again, that can also trigger a tier up. And so here we're just forcing it to be optimized as quickly as possible. Then we have this return array -3 plus array 2. Not all that interesting. It's not quite clear what's going on. These floating point values, 3.544, blah, blah, blah. If we were to look at the floating point representation of that, it ends up being that those are upper bytes are all zeros, and then the rest is 41, 41, 41, 41. Oops. And then we have this var array, which is going to be an array with contiguous, which just has string values. And if we look at what's actually going on, we have one of the phases that's being iterated through, the integer check combining phase. And so this is the phase that is responsible for removing array bounds checking. We have this case that's specifically doing that. And assuming we actually hit this, we'll go through and we'll remove nodes where checks are going through. Looking at this function a little bit more deeply, we have this if-else, and here we're setting the min node to 0, and then we are setting the max node to whatever it is. So in the case of array accessing -3, it's going to set the minimum value as 0, and it's going to say that max value is -3. And then it's going to insert that with a check and bounds operation using that value, using that -3 value. The whole issue here is that, as I was mentioning about the FTL earlier, the FTL only deals with signed integers. So when it goes here to do this check above or equal, it's going to say is 0, or is the length of the array above or equal a signed value. That ends up basically being a lie, and you're able to read and write around the contents of memory right before the buffer. So if we go back to, should arrange this better. if we go back to this array, what's going to happen is when we access the array with contiguous array, we're going to access the values in array 1, and we're going to get an out-of-bounds read to the preceding array, and those are going to be dereferenced and treated as pointers to JS values, and we're able to leak memory and then craft our own pointers based off that. Go past. Cool. Next vulnerability I'm going to cover is CVE 2018-4162. This is one that I found kind of by accident. What happened was I was at home just looking at a Stack Overflow article, and someone was on Reddit posting to someone. Sorry, I was looking at Reddit where someone had linked to a Stack Overflow article, and basically someone had a job interview. They were JavaScript dev, web dev, and they were asked as an interview question, can A == 1 and A == B and A == 3 ever be true? And they had no idea how, but it turns out you can because JavaScript has two different types of equality. There's a notion of loose equality comparison, so 1 is equal to true, and 1 is equal to a string that contains 1. What's going on here is that JavaScript is seeing, hey, these are two different types of values, and we want to see if they're true. We're going to do a type coercion on them, and if the resulting value is equal, then we'll treat it as equal. And then there's strict equality, which has, in this case, 3 equal signs, where it will do a type check before it actually does any comparison. If they're not of the same type, then obviously it's going to fail. And if they are, then it'll return true or false. And so I did a quick test just with this, just to verify my assumptions. So here we have 1 ==, and then we're crafting an object with a custom value of function. You can also use toString. Either will work. And within the toString, within the value of function, we're just printing, hey, we got called, and then returning a value. And this is all just saying that, hey, when it actually did the comparison, it saw that we got, or it'll try to do a type coercion, and then it'll continue on. I ran a quick test with that, now modifying it and seeing if I could force a crash, this time trying to trigger type confusion, and I was able to get a crash. Looking at the trigger, I'll go over basically all of this. We start off with an array that is an array with double. And then I'm going to call it a stupidly large number of times just to force it to be DFG'd. It actually goes into FTL. Doesn't really matter as long as it gets DFG'd because that's where the vulnerability itself exists. And then we have array 0 and array 1. OK. We have array 0 and array 1, or A0 and A1. We're just going to write floating point values to it. And then we're going to call C == 1. We're then writing this value, and I don't remember what value that is. Basically, it's a decimal value that can be interpreted as a floating point, as a pointer, just to try and prove out that we can do something interesting. And then in between that, we're calling C == 1. So when we actually call it that one last time, we're going to call it with array 1. We're going to call it with a custom object with a custom toString function, where we are changing the type. And what's going to happen is all of those values, the 1.1 and the 2.2 that got written, as well as the 3.3 that was there from the get-go, those are all going to be converted into tagged double values. So they'll have 2 to the 53rd power added to their value. And then we'll return 1. But that last write at array at index 2, that's going to write just that floating point value, such that when we then do this string plus array 1 at the second index, it's going to crash, and it's going to dereference the value of our choosing. If we look at what's going on within DFG clobbereyes and DFG abstract interpreter inline, we'll see a block that looks similar like this, where they have a bunch of checks, but all that's really happening is they're seeing, is there any way that they can mark this as a constant operation for performance reasons? There's no checking to see, is this going to be a situation that may result in actually calling JavaScript, which may break assumptions. I'd mentioned that JIT bugs are great for leaking information. Here's an example of doing exactly that. We start off with basically the exact same proof of concept as before, but now we have a float64 array. We have a couple of helper methods that will just take a floating point value and convert it into integers and back. And then all we do is replace that last call at the end of our go function with a read from array 0, and then write it back out to this floating point array. So now when once we've triggered the bug, we can take that value, convert it into a quad value, and now we have an idea of where objects are laid out in memory so that we can craft our own, trigger type confusion, do all sorts of things. As far as variants of this go, there are a ton of them. There were a ton of them, probably fewer now. I think I had submitted 5 different vulnerabilities here. And an interesting thing is that if you look at some of these versus what was in Chakra, over the years, at least the last 2 years or so, they've had very similar vulnerabilities, almost the exact same in a number of cases. But the nice thing here is that once you've written an exploit for one of them, you've covered basically all of them, and swapping them out to get a new fresh exploit triggering a new vulnerability is very, very nice and straightforward. And to that effect, we have a spread operation, which I believe also hit Chakra. Math.clz32, this is the one that I opened with in that first snippet of JavaScript code. Math.absolute, and each block here is a separate switch case within the DFG clobbereyes and within DFG abstract interpreter. Math.round, floor, seal, trunk, and then this giant mess. And it's just really nice from the exploitation standpoint because, again, it is very, very straightforward. Not nearly as nice from the point of view of anyone that ever has to use any of this functionality because, well, it just makes it entirely too easy. And on that note, finishing entirely earlier than I expected, but if anyone has any questions, please let me know. One thing I really like about the JIT engine across all the interpreters is that although it makes things very, very performant, there's a lot to consider as far as the security goes because any sort of mistake is great for exploitation and not at all good for anyone that actually uses things. There's also very much similarities, specifically within Chakra and Safari, less so with Chrome or V8 and SpiderMonkey, but there are still some, and it can be a lot of fun. DFG still remains the most vulnerable, the most heavy-hitting as far as vulnerabilities go. The FTL vulnerabilities have mostly been one-offs, and that's about it. Thank you for your time.